Welcome back to ECE 320A. We finished exam number 2, or you have completed it, and now we're moving on to the next chapter in the textbook, which is chapter 13, and this has a lot of useful material in it, and one way of measuring that is through homework assignment number 6, which is due in a week. That's due on April 2nd. And I think we have 2 more homework assignments after that prior to exam number 3. But that's where we're headed. We're headed into chapter 13, and it will be performing S-domain circuit analysis directly, meaning we don't have to write the differential equations and then Laplace transform those. We're going to immediately write down the S-domain equivalent circuit and do the analysis in the S-domain, which really means now we simply are performing algebraic operations. The algebra will be involving complex variables S, and we'll be playing with these polynomials, but you know how to play with polynomials in the form of inverse Laplace transforms to get back into the time domain. And we'll try to motivate that today and give an example. And I want you to hopefully have a better understanding of how you can now incorporate or account for the initial conditions on any L's and C's that might be in your circuit in the S-domain equivalent. And you'll do that by introducing sources. So let's see if we can motivate this concept, which is from chapter 13. It's S-domain circuit analysis. And suppose that we now are given this RLC circuit, and I'll give you time to maybe kind of sketch that, and as you're sketching it, maybe you're thinking about it in terms of what it might do or what you might be expecting in terms of the analysis that results from that circuit, and in particular, how might one find this voltage V sub 2 of t as a function of time across that second resistor R sub 2 for some input voltage V sub I of t? That's really what we want to be comfortable doing, is can we now find any variable in this circuit? It could be a current somewhere, it could be a voltage somewhere else, but let's just sort of put it on the farthest side of the circuit in this case, V sub 2 of t. And now how does V sub I of t influence V sub 2 of t, and how is V sub 2 of t determined based on this arrangement of circuit elements? And if you're looking at that circuit, based on how you would analyze it now using chapter 12 material, what are you thinking you might be looking to see or create in terms of the analysis? Pardon? So now you're looking at maybe a second degree, 2 first order differential equations. You're thinking in the time domain. You have 2 energy storage elements, and that's what's making you think I have now a second order system. And that's a valid way of thinking about what to anticipate or think. So using what we've done in the past, or up to this point, you might write 2 integral differential equations and then if one of those, let's say that you love to write mesh equations, and one of those currents, you now found the current in that second mesh, now you could write or find V sub 2 of t simply by scaling it by the resistor R sub 2, since you know Ohm's law. V sub 2 of t is just R sub 2 times I sub 2 of t, if I sub 2 of t is the current in that right mesh, if we were doing mesh analysis, for example. So if one of these equations that you're looking for 2 or a second order, if one of these equations involves the current in the second mesh, then we have it. Then we know that we could simply find V sub 2 of t by scaling that mesh current I sub 2 of t by the resistor R sub 2. And then we have V sub 2 of t. If that's the way that we solve this or approach it, then we're looking at solving either a second order differential equation or 2 coupled first order differential equations. We must solve a coupled set of differential equations. Suppose now you go, oh, but I've had 320. So now after today's lecture, you're going to go, oh, but I have another strategy or another approach to solving that circuit problem. And in particular, maybe that circuit problem was given to you in the textbook or in your homework, and you say, well, let me write down the S-domain circuit associated with that original circuit. And you would say, oh, I had a voltage source on the left. Let me now just capitalize that and give it an argument of S. That's now in the frequency domain. I had that connected to the first resistor, R sub 1. And then I had a capacitor. And in fact, we will learn that the impedance of that capacitor, now we're going to write these circuit elements in the form of their impedances. We have R sub 1, the impedance in the S domain of a capacitor is 1 over SC. And in fact, we would then know to do the following. We would say, oh, we have an initial condition on that capacitor of value V sub C of 0 minus, and we would put in a source with the appropriate polarity label. Then we would say, well, there was also an inductor, and that inductor now has an impedance of S times L. And we're going to derive where these come from, but now we can simply start re-sketching that original circuit, and now we actually have a voltage source that accommodates or accounts for the initial current that's flowing in that inductor. This one is a little different than the voltage source associated with the capacitor, since they're two different, their impedances you can see are reciprocally related. We now have the inductor value times I sub L of 0 minus, and then we have our resistor R sub 2, and here is maybe our variable that we wanted to focus on in this particular circuit, the output voltage, and this is now in the frequency domain. This is the S domain version of that voltage across R sub 2. And what you can see, I think clearly, is there is a little structural difference now between this circuit and what we had before, and that structural difference is due to or resulting from these new sources that we've introduced. And so you might be saying, why are there those voltage sources? You can kind of see that they are labeled with these initial condition values, and they have an S and no S in some of them. Question? So the question was, is that a voltage source or a current source next to the inductor? The way that I have introduced these today in this part is that's a voltage source. And now you're probably saying, but you said to focus on currents with inductors. Yes, that's true, but we will learn how to either incorporate these initial conditions as series voltage sources or as parallel current sources, depending on what kind of an analysis you want to perform. Here I'm saying, oh, we like mesh analysis, so let's not disrupt the two meshes that we had to begin with. And if we want mesh analysis, then we're going to incorporate voltage sources. If we were doing nodal analysis, then we would be putting current sources in parallel with the capacitor and the inductor. But in this particular circuit, I've deliberately introduced a voltage source so that I still have not introduced another mesh in this particular circuit. I still have two meshes that I will perform the analysis with. So let me just say, if you're reading this after the fact, let's just now say, well, why are there voltage sources in series? They're introduced in a particular configuration. They're in series with these two energy storage elements, a capacitor and an inductor, with the energy storage devices or elements. And maybe I'm getting a little wordy, but let me just go ahead and write down what I'm wanting you to sort of remember. The voltage sources in series with the L's and C's in this S-domain circuit account or take into account for the initial conditions on the energy storage devices. And if we're full of questions, it's a new week, maybe we are still sort of thinking, well, I'm not quite sure where this is coming from. So you might say, well, how did that happen or why? And we'll simply go back to what we know. We know Eli and ice. And let's just look at ice since it's so hot today. Maybe you're wanting to focus on ice initially. We'll look at ice, which is associated with a capacitor. Let's recall the current voltage relationship of a capacitor. And that is I, the current associated with the capacitor, I sub C of t, is C dV sub C of t dt. And I hope it's not a stretch to realize that that's in the time domain. That's the time rate of change of the voltage across that capacitor influences or is proportional to the current induced in that capacitor. And the relationship between those in the time domain, well, yeah, there's a capacitor. Good weekend. Capacitor, now we have our voltage, V sub c of t, and the passive sign convention says that this is how we would label that time domain capacitor's voltage and current to be consistent with this ICE formula. I is equal to C dV sub C dt. That's the connection. Suppose that we now Laplace transform this time domain expression. You can do that now. You know how to Laplace transform derivatives. And in this case, we want to account for any possible piece that might arise, and in particular, capacitor, it's an energy storage device, it could have an initial condition. Let's then do the Laplace transform of a derivative and incorporate or keep track of the initial condition. Laplace transforming, the left side's pretty easy. We just have to hit the shift key. That's just capitalizing or taking the Laplace of I sub c of t is now I sub c of s. And now we need to Laplace transform the right-hand side. C, the Laplace transform is a linear operation. We can keep that C outside of the Laplace of the derivative of the voltage. And we now have C times S, V sub C of S. That's the capital V sub C is the Laplace transform of the capacitor's voltage. Multiplication by S is what happens in the frequency domain when we differentiate in the time domain. And then we need to subtract off the value of the initial voltage across that capacitor. That's a time domain value, minus V sub C of 0 minus. That's what the voltage was across that capacitor at 0 minus. We can distribute that S across both terms on the right-hand side to yield SC times V sub C of S minus C V sub C of 0 minus. And now, since we were writing this in terms of mesh analysis, we want to essentially relate the voltage across that capacitor in terms of the current and the initial conditions. Let's now isolate for or on the Laplace transform of that capacitor. It's voltage, which means divide every term by SC and add that initial condition to the other side, and I'm going to go ahead and move the capital V sub C of S to the left. And what now scales I sub C? I've divided everything by this product SC, and now I have multiplying I sub C is 1 over SC. Are we comfortable with where that came from? Divide everything by SC, and hopefully you can see that V sub C is now by itself if we deal with the initial condition later, but we have 1 over SC scaling I sub C of S. And if you think of V is equal to Ri, or Ohm's law, this is a generalization of that. This is V is equal to Zi, where the impedance of the capacitor is 1 over SC. You could say, that's Ohm's law. V is equal to Zi, where Z is Z sub C, and that's 1 over SC. If we now add C, V sub C of 0 minus to both sides and divide by SC, do you see that the C's cancel? And we have then plus V sub C of 0 minus over S. This is now our impedance associated with a capacitor in the S domain, and this term is due to our initial condition. And you know what that looks like, or what that corresponds to in the time domain. What's 1 over S in the time domain correspond to in terms of a waveform? A constant. That's a unit step, isn't it? So this is really in the time domain a scaled unit step, and that's how we account for the initial voltage on that capacitor. This is now our initial condition term, and this equation we've now moved into the frequency domain. And now let's draw this equation as a circuit. We now have the voltage across the capacitor really consisting of two terms. One term is due to the impedance of that capacitor, and another term is due to the initial conditions. It's a series connection making up that one voltage across your capacitor. Or you could now draw this as a circuit element in the following way. You could say, okay, I have a voltage source and I have a capacitor. What's the impedance of that capacitor? 1 over SC. And suppose that I now say, oh, my current is coming in here. That's the current associated with that capacitor. The voltage, in fact, is associated with both of those elements. Here's V sub C of S. And how do I label that series voltage source? Well, it needs to be labeled in such a way that it's consistent with this equation. If I sub C goes through this capacitor that has an impedance of 1 over SC, do you see that we now have 1 over SC I sub C coming in, or on the right-hand side? Or another way of looking at that is you could say, you know what, maybe you've done this in 220, you say, let me just write a KVL associated with this particular circuit, and you start here and you now just go this way. Or you now say, oh, I have minus V sub C of S, and this is how we will figure out the polarity. Let's say this is now plus minus, and this is V sub C of 0 minus over S. That's now plus V sub C of 0 minus over S plus 1 over SC I sub C of S, and then we're back at where we started. If you now add V sub C of S to both sides, do you see that we've now just rewritten this equation that we obtained by Laplace transforming the time domain ice relationship? And that's now how you could check to say, oh, what's the polarity on that voltage source associated with a series, or when it's in series with this capacitor. We know the impedance of the capacitor, that's 1 over SC. Suppose I had 0 initial condition. What would we do with that voltage source? So now what happens when you zero a voltage source? So what happens when you zero out a voltage source? It becomes a short, doesn't it? It's a wire. So now if that was a short, you wouldn't have that voltage source, but you wouldn't open your circuit up. You would now just have your impedance of the capacitor. So if you had zero initial condition on that capacitor, you could essentially not worry about that voltage source and replace it with a short. We okay with how that now arises relative to ICE, or the voltage current relationships of a capacitor. And what you can do tonight is you can say, I don't want to play with voltage sources, I want to play with current sources. Then you would want to solve this, or just use the original form that we had. We had I sub C, the total current through the capacitor, is now made up of two pieces. One piece is associated with the impedance, and the other piece is in parallel with it, and it is due to this initial voltage. So even though it's a current source, it has a value determined by the voltage initial condition on that capacitor. For now, let's just focus on the series equivalent S-domain circuit, and that's now what we've sketched. And this should be consistent with what we did here. If we then had that voltage initial condition on our capacitor, we now have a plus minus, and you can see it doesn't really matter whether the voltage source is below or above the capacitor, the analysis will be the same, as long as it's in the same series branch. What about these resistors? So that's how we can justify the S-domain equivalent circuit for a capacitor, any capacitor. What about a resistor? We have Ohm's law, which looks just like V is equal to Ri in the time domain, where V is a function of time, I is a function of time, the current and the voltage are just proportionally related. That's Ohm's law. What if we now Laplace transform that? Shift key. Yes. We don't have to do anything really other than capitalize those variables and make sure that our arguments on those variables are now in the S domain, or a function of the complex variable S. We now have capital V sub R of S is equal to R I sub R of S. And in this case, if you have a resistor or resistors in a time domain circuit, you can put those right in the S domain equivalent circuit in the same way that they were inserted in the time domain circuit. Or what I will say is that resistors actually carry over to the S domain unaltered. Or the passive sign convention with this, or any resistor, is consistent with what it is in the time domain circuit. What about an inductor? And now I could actually ask you to do this on your own. So now you can beat me to the finish line. What if we were dealing with the inductors? What's the first thing? We have Eli, and Eli tells us the current voltage relationship of an inductor. V is equal to L di dt. We have V sub L of t is equal to L di sub L dt. That's in the time domain. We Laplace transform that. We have capital V sub L of S is now L times S I sub L of S minus I sub L of 0 minus. And if we distribute that L through the two terms on the right-hand side, we now have SL times I sub L of S minus L I sub L of 0 minus. And that term or expression that is now scaling the current in the S domain is the impedance of our inductor. And the other piece, which we could incorporate that minus sign in the polarity labels of our voltage source, but this is now a voltage source in series with that impedance that creates the overall voltage drop of our inductor. And these are now our initial condition terms. So that if we wanted to compare these in the time domain, there's L, and here's V sub L of t. Passive sign convention, there's I sub L of t. This is now the time domain circuit diagram. In the frequency domain, what does it look like? Now we don't have to solve for anything. It's already V is equal to something, some impedance times the current, plus a term due to the initial condition. So this is now already in the series form that we need it to be in. Or we have an impedance. We know what that is. That's S times L. Anytime you have an inductor and you want to go into the S domain, you can simply say, oh, I have an impedance, SL. Let me put it up above since I'm going to do my voltage. And then I have a voltage source. And maybe I don't know what the polarity labels are on that just yet, but I have a current, I sub L of S, and the voltage dropped across that inductor is made up of two terms. And again, if I do the KVL around this, I could go this way, and I could say, oh, minus V sub L of S plus SL I sub L of S. And now what do I want to do? I now need to have a minus L times I sub L of 0 minus. And let me just put the minus sign into the polarity of my voltage source. I now have minus plus, and the value of that voltage source is now L I sub L of 0 minus. And what kind of a time domain waveform does that correspond to? What happens when you inverse Laplace 1? What happens when you guys got this right, I think, on the exam? It's an impulse, isn't it? A constant in the frequency domain, a 1, corresponds to an impulse. So here, the initial condition on that inductor is being created with an impulse waveform in the time domain. That's how we energize that inductor to establish its initial condition. And we do it in the frequency domain by this particular voltage source in series with the impedance of the inductor, which has an impedance value of SL. But do you see that this voltage source creates or brings the initial condition in a slightly different functional form than the voltage source of the capacitor? This one is just a constant, L times I sub L of 0 minus. The expression that weighted the voltage source, the series voltage source associated with the capacitor's initial condition, is now V sub C of 0 minus over S. There's no C in that, and there was an L in the inductor. So you have to keep track of these when you want to push these particular elements through into the frequency domain. Questions on those equivalent circuits in the S domain and how they arise. Now we have this circuit. We should be able to analyze it. Suppose, since I kept it in meshes, let me say here is I sub 1 of S, and here is I sub 2 of S. And now I want to solve for I sub 2 of S, because if I know I sub 2 of S, I can immediately find V sub 2 of S, because it will just be a scaled version of I sub 2. And why do students really sort of like Chapter 13, or this part of Chapter 13? I better not claim they like the entire, well, you'll really like Chapter 13. But now, you've basically converted these differential equation problems back into equivalent problems that you solved in 220, but now your resistors are generalized resistors. They now have impedance values. And as long as you keep track of those, as long as you keep track of the S's, you can now just do algebra like you did algebra for your all-resistive circuit analysis problems. Which means we should be able to solve for I1 and or I2 in this circuit by simply doing some algebra. And let me now try to write that down. Let me say that, how do we solve? Well, we simply find I sub 2 of S. That's the mesh current, one of the mesh currents. And determine V sub 2 of S from I sub 2 of S, just by scaling it by R sub 2. And I'm saying that now that we have this circuit with the initial conditions incorporated, we can do this by inspection. We can write down two equations and two unknowns by inspection. We don't have any dependent sources, so the inspection process is quite easy. Did you do mesh analysis by inspection in 220? What do you mean by inspection? So I'm guessing you didn't do it. So what we can do is we can look at this circuit and immediately put it into a matrix representation that gives us two equations and two unknowns. And what we're going to do is we're going to have in this case, since it's mesh currents, we're going to have some matrix times our unknown mesh currents, I1 and I2. If we have a matrix times I's, then that matrix is actually impedances, then we would expect the right-hand side to be consisting of voltages. And on the right-hand side, we will somehow figure out how to put these voltage sources, those are the sources that force our circuit or force these currents to flow in mesh 1 and mesh 2. Here's what we're going to do. Suppose I now want to write the top row in this impedance matrix. let me first, let me scroll down quickly, so close your eyes if it bothers you. But now what we, oh, are you kidding me? Close your eyes again, don't fall asleep. I have to watch how I touch this. So because there were no dependent sources, we're going to do this by inspection. We can do it by inspection with dependent sources, but you just have to be a little bit more, what do I want to say, observant of what you're doing. What I'm now saying is we have some matrix, and I hope I can make this the correct size, times I sub 1 of s, I sub 2 of s, and that's going to equal some collection of voltage sources on the right. This all has to be compatible, which means that this better be a matrix which when multiplied by a 2 by 1 vector gives me a 2 by 1 vector. Or this matrix is a 2 by 2 matrix, where this is now our impedance matrix. And this is our source matrix, or right-hand side. Let's see how we can populate this matrix. Let's start with the 1, 1 element. The 1, 1 element is going to be these impedances that all multiply I sub 1. If we go back to our circuit, and let's now just think about writing a mesh equation in mesh 1. What happens? Well, if we started at the lower left, we would have minus V sub I of s. Then we would say, oh, plus R1 times I sub 1 of s. I1 touched R1. So keep that in mind. I1 touched R1. It now does what? We would then say 1 over SC times the net current down, which was I1 minus I2. And we would have no more impedances that current touched. What was the sign on all of those terms that I1 touched in mesh 1? Is that a question or an answer? I'm only accepting, no, go ahead.
So what about the voltage of the capacitor?
So now we'll talk about that later, but in the KVL, if we were writing a KVL equation, we would say, oh, plus V sub C of 0 minus over S. So we had minus V sub I, and now we had plus V sub C of 0 over S. Now while we're here, so those are the sources. If I increased V sub I, would that tend to make I sub 1 bigger or smaller? If somehow I could build up the potential on V sub I, would that make I1 bigger or smaller? Make it bigger, wouldn't it? So keep that in mind. If I increased V sub C of 0 minus, or made that voltage source bigger, would it increase or decrease I sub 1? If I really raised this up, it's kind of opposing I sub 1, isn't it? So it would tend to decrease. What I'm trying to say is by inspection, you could say, oh, on the right-hand side, V sub I, since it's enhancing I1, it will come in with a positive sign. And this voltage source, V sub C of 0 minus over S, since it opposes I1, it's going to come in with a negative sign. If you just write KVL, you can put it into the matrix structure. I'm just giving you another way of thinking about this. So don't think you have to do it by inspection. You can just write the KVL equation, which everybody seemed to be comfortable with. Now let's see how that flows into the matrix. We look at all of the impedances that I1 touched. That was R1 and 1 over SC. We just add those up and we put that in the diagonal element of the matrix associated with I1, and that's the 1, 1 element. We say, okay, put all of the impedances touched by I1 in the 1, 1 entry of this impedance matrix, and what I just said that was 1 R1 plus 1 over SC. Now, which impedances were shared between I1 and I2? 1 over SC. That now comes into the off-diagonal entry with a minus sign. When we were writing it, it was 1 over SC times I1 minus I sub 2. We're just going to incorporate that minus by saying, oh, we had a common impedance shared between I1 and I2. That's what's going into that off-diagonal entry. That's shared between I1 and I2 because it's element 1, 2. It will now have a minus 1 over SC term. What did we say was on the right-hand side? 2 voltage sources. Capital V sub I and the voltage source associated with the capacitor. V sub I enhanced I1, so we'll write that as V sub I of S with a positive sign. And the initial condition, it opposed I1. This would be minus V sub C of 0 minus over S. By inspection, we wrote down that top row in this set of in this first equation. Can you now write down the second row using the same process? Well, if that's true, if we can follow this process in this location, that means we better put in all of the impedances that I sub 2 touches. The sum of those. I see it touching 1 over SC, I see it touching SL, and I see it touching R sub 2. That's now in the 2, 2 entry of that matrix. What impedances shared or impedances are shared by I1 and I2? 1 over SC, that's going to come in with a minus sign in that location, the 2, 1 entry of that impedance matrix. And what about our voltage sources? What do we do with V sub C, the capacitor's voltage source? If we increased it, would it enhance I sub 2?
Yeah.
Yes. What if we increased L I sub L of 0 minus? Would it increase I sub 2? So now I'm just saying, look at the polarity on that source and say, okay, if I made L I sub L bigger, would that make I sub 2 bigger? Yes. So those 2 voltage sources are going to be coming in with a positive sign on the right-hand side of that second equation. I'm ready to write down by inspection what I just said, hopefully. I have the sum of all of the impedances that are touching I sub 2. That's going in here. And that was 1 over SC plus SL plus R sub 2. What impedances were shared by I1 and I2? Those sum up and come in with a negative sign in the off-diagonal term. That's this minus 1 over SC. The source term now becomes V sub C of 0 minus over S with a positive sign, and L I sub L of 0 minus comes in with a positive sign. And now we have our analysis ready to be just put into a machine and cranked out. We now have all of the dynamical equations associated with that second order RLC circuit now in one matrix equation. Zi is equal to V in general. Ohm's law. How do we solve for I sub 2 of S? So you could do KVL on the right side, but now that we have it in this beautiful form, put it in your calculator. Okay, fine. But what if you had this in a math class and somebody gave you a 2 by 2 matrix? They said AX equal B. Put it in your calculator. You could do row reduction. Boy, you guys are learning your 310 or your linear algebra, but if you go back, you could say, well, I could also do this using Cramer's rule. Do you remember Cramer's rule? It's a ratio of determinants. If you don't want to invert that impedance matrix, if you inverted that impedance matrix, you would be solving for I1 and I2, and you would have both formulas. You would have a formula for I1 of S and a formula for I sub 2 of S. Suppose we just want I sub 2 of S, a formula for that. Well, that would just be Cramer's rule, which is a ratio of determinants. The determinant downstairs is the determinant of the A matrix, which in this case is the Z, the impedance. We'd take the determinant of that. And you can do the determinant of a 2 by 2 matrix. Product of the diagonal minus the product of the off diagonal. What's upstairs for the determinant? Well, it's this impedance matrix, except we're trying to solve for I sub 2. Well, then we replace the second column in that Z matrix and replace it with the source. And we form the determinant of that. That's Cramer's rule. You want to do the limiting case? This is, we have to be positive, right? But we now have a way, a brute force way of solving this. That now avoided doing any differential equations. We've now done linear algebra with this frequency variable S. We now have a ratio of polynomials in S. Let me write down what I tried to just say. Cramer's rule would be, for solving for I sub 2, we now have the top, and that's what I'm going to say are these vertical bars, the determinant. The first column is just the first column in the Z matrix. That's R1 plus 1 over SC. And then it was minus 1 over SC downstairs, or in the second row of that first column. Since we're solving for I sub 2, we replace the second column in the A matrix, and we replace it with what is on the right-hand side, the B matrix. We now have V sub I of S, and you know what that looks like. If it was a sinusoid, cosine. Pure cosine, it would be S over S squared plus omega squared. That's capital V sub I of S. Boom, that goes in there. Then we had minus V sub C of 0 minus over S. And in the second row of that right-hand side, we had V sub C of 0 minus over S plus L, I sub L of 0 minus. Whatever the initial condition was on that capacitor, let's say it was 6, we now have 6 over S. Let's say we had an inductor value of 1, big inductor. We have now 1 times whatever the current was. Let's say it was 10 amps. Oh, be careful. That'll kill you. Divide it by 1,000 and it'll still kill you. So 10 milliamps you don't want to play with. But anyway, that's what you would put in there, just a number. And you could now find that determinant. You divide it by the determinant of the impedance matrix, which was R1 plus 1 over SC minus 1 over SC. And then this was minus 1 over SC. This was just the second column of the impedance matrix, R2 plus SL plus 1 over SC, and take the determinant of it. Well, now that you guys are experts, let's do the following example. Let's just ratchet it up a little bit. Suppose now I give you the following circuit. Here's a capacitor. Let's say I have a resistor here. Let's say I have an inductor here. Let's say I have a resistor here. Let's say I have a switch there, and this is now going there. And let's say we have a resistor here, an inductor here, a resistor there. Why are you laughing? You're now experts. So now we have a capacitor here. We have a switch, and let's say we have a current source here. And this was V sub 1 of t. And let's say this is 4 Henry, 1 ohm, 5 farads. This is now 3 Henry, 2 ohms, 5 ohms, 6 farads, and let's say this is 8. And suppose that this switch opens at t equals 0. Pardon? A lot of farads. Oh, forget the farads. Just keep track of them. That is a lot of farads, but they now have supercapacitors. You can do some damage with supercapacitors. Let me show you what V sub 1 of t is. If this didn't make you nervous, let me try to make you even more comfortable with what I'm going to say is V sub 1 of t. Or actually, how do I want to say this? Yeah, let me say V sub 1 of t is the following. V sub 1 of t, suppose that it's constant, and then it becomes sinusoidal. And that's actually a cosine, if you couldn't tell. This, let's say, is cosine of 5t. And let's say it had a magnitude there of 1. This is now V sub 1 of t. Or as a functional form, V sub 1 of t, how would I write what's happening from t equal minus infinity up to 0 as a standard waveform expression? It's a unit step, but it's backwards, isn't it? So how do we turn a unit step on for negative time? A unit step for positive time is u of t. And that now says I'm 1 as long as my argument is non-negative, u of t. Now I want that to be 1 when my argument, or when t is negative. Well, if I do negative t in my argument, then it will be on for all negative t. Meaning, this straight line we could write as a function, as a standard waveform, as a unit step of minus t. Then it stops for positive t. The argument is negative, so it shuts off. And we have to now create V sub 1 of t with another piece that is only on for positive time. And we have the functional form, that's cosine of 5t. Am I done? I need to turn this one on for positive t, so I need to switch that with u of t. And suppose somebody didn't label that cosine of 5t. How could you figure out what you had if they had a sketch of it. How would you determine? One, you would say, well, it's cosine because it's maxed out at time t equals 0. That's where it's hitting its maximum, and cosine of 0 is 1. Now, how do I find, so its amplitude is 1 cosine. How do I find that that's actually 5? If I didn't know that it was 5, how would I determine that the frequency was 5 radians per second? From the sketch. I've sketched it accurately, let's say, and I've labeled the time axis accurately. You could measure the period, couldn't you? You could get out your ruler or whatever drawing instruments you need and find the next maximum of that cosine and put a vertical line down to the time axis. That now gives you the length of the period. Once you have the period, now you can find omega. Omega, so what I'm trying to say is if you now measured this distance, that would be t, and you now know that omega is 2 pi f, but that's just 2 pi over t. And once you now have measured t, you could now solve for, why do I have to do that? Plug in t and you have omega. In this case, if we know omega, you could now solve for t. T would now be omega, 2 pi over omega. And if omega is 5, how big is the period? 2 pi over 5. What's 2 pi? Tasty if they're good pies, but 2 pi is a little bit bigger than 6, right? 6.28. So 6 over 5. 1.2 roughly, a little bigger than 1.2. That's the period that you would be measuring. All right. Where were we? Now, what I want to do is if you looked at this, if this was now on the final exam, question? V1 of t.
So if I'm saying the unit step right, what you drew as its wave function and the equation you gave us, do they have the same value at time of 0?
Yes, so now what we're going to assume, the question was, you're wondering if they are consistent or compatible at time 0. And what I'm going to say is, let's let u of t be, how do I want to say this? Only have a value, a non-zero value, when the argument is non-negative. So now let's forget at 0, Because what do I have? I kind of have a 2 right there instantly. So let's just assume that u of minus t, we're only going to say, just stay away from 0, and we'll throw you away at 0. Is that okay? In reality, we would have a bump up of 2, but that really wouldn't change anything in our analysis. That's a value of 2 instantaneously, and that's not really going to mess or influence our circuit. Because we're now we really are trying to establish initial conditions in this circuit by having, for t less than 0, can you sketch what this circuit looks like? You did it on the exam. What happens for negative time? Do we have a current source active for negative time? Yes, so that's active. Do we have a voltage source? Yes, it's 1, and our current is 5. What happens to the capacitors and the inductors? We open up the capacitors and we short the inductors. So now we can re-sketch this for negative time to establish the initial conditions. Suppose that I now, well, so let's say we now want t less than 0, strictly less than 0. We're doing this to establish initial conditions. The circuit now has a 1 there. I'm assuming my impedances are correct. Then we had a capacitor that opened, and let me call that, did I have 2 capacitors? Did I label them as C1 and C2? Let me call this C1 and this C2. And let me call this L1 and this L2. And suppose this is I sub L1. This is I sub L2. And this is now V sub C2. And V sub C1. Let's now try to sketch where those are in our circuit for t less than 0. The inductor's short and the capacitor's open. We now have V sub C2 of 0 minus. We have a 2 there. We have our current source here of 5 amps. We have a resistor of 8. And then this was 2. And up here was our first capacitor that's now opened up. Oh, and I need to label my inductor currents. Here's I sub L1 of 0 minus. This is I sub L2 of 0 minus. This is now a 220 problem. It's just a resistor with some sources, a voltage source and a current source. And you can now solve for these currents, and then once you have the currents, you can use those to try to figure out what the voltages are in the appropriate air gaps. Did Dr. Marsland say voltages across an air gap? Did you solve for those in 220? Ooh, that should be fun, right? So we just write KVLs and figure out what those particular voltages are. What if I now performed KCL over here? Let me call this node A. And let me say that I'll just label this V sub X. I really just have 3 currents to worry about. The one going to the left horizontally, the current source is coming up, and then I have a current, let's say, going down vertically from node A through the 8 ohm resistor. And that's V sub X over 8. The current going horizontally, let's say out of node A towards this voltage source, it would be the voltage dropped across that resistance, which is 2 plus 1. So I now have that voltage drop divided by 2 plus 1, and that's the current going to the left. So KCL at A says I now have V sub X minus 1, because of the voltage source on the far left, divided by 1 plus 2. Then we have a plus V sub X over 8. Those 2 currents are flowing out of node A, and flowing in is 5 amps. I'm assuming you've already pulled out your calculator. and found that V sub x. It's 128 over 11. If that's the current, I'm sorry, that's V sub x, and now we can find I sub L1 of 0 minus, which is the same as I sub L2 of 0 minus, isn't it? But I sub L1 of 0 minus is just going in the opposite direction horizontally. It's 1 minus V sub x over 3. And we just found V sub x, and this now becomes minus 39 over 11, and this is I sub L2 of 0 minus. We've now found the initial currents. We can find V sub c sub 2 of 0 minus doing a KVL here in this left mesh. That's now minus 1 plus I sub L of 0 minus times 1 plus V sub c sub 2 of 0 minus is equal to 0. And this we just calculated to be minus 39 over 11. The only unknown in that equation is V sub c sub 2 of 0 minus, and if you solve it, hopefully you'll end up with 50 over 11. And finally, we have this mesh right there. Or, let me say that's the top mesh, which is, if I go in the way that I did, it's minus V sub c1 of 0 minus plus I sub L sub 2 of 0 minus times that resistor of 2. And then what? Then I'm actually back where I started, since that was just a node A. So that is equal to 0, and I can solve for, this is the same as what it was before. This was minus 39 over 11. And this now becomes minus 78 over 11. We have all of our initial conditions, 4 of them. 2 inductor currents. Is that a question, or are we exercising? Question? Okay. Oh boy. You're going to have to speak louder than that. What? Was there a 5 ohm resistor in the top mesh? I don't know. Was there? You're asking me? I wrote this down about 30 minutes ago. I don't remember. Yes, there was. What happened to that? If the capacitor opens up, how much current is flowing through that 5 ohm resistor? 0. So we could put it in there and we'd have 5 times 0, and it won't matter. So we could worry about the drop across that 5 ohm, but there is no drop because it has 0 current flowing. Does that answer your question? So we have a few more hours. Let's now work this out. That wasn't a joke. I've reserved this room actually now. Tonight I do have this room. Is anybody going to stay here with me? So now at t greater than or equal to 0, we can now write down the S-domain circuit. Yes? And what's it going to look like? Now we do have to keep track of that 5 ohm resistor up in the top branch. we would have a capacitor. And what's its impedance? 1 over SC, whatever C was, which was 6. So this is now 1 over S times 6. And we have a voltage source, which is plus minus with minus 78 over, well, it was minus 78 over 11 divided by S. And that's its initial condition incorporated into a series voltage source. I'm going to move that 5 ohm resistor up here. And that's now the top piece of my circuit. The current source goes away because it was only, the switch opened at time 0. I now have an inductor and its voltage source to accommodate its initial condition. What's the impedance of that inductor? And the generic answer is SL, right? And we just have to remember what the L was, and that was 3. So this is now 3S. And we know what the initial current was, and we can now say that that's L times that initial current, which was, in fact, minus 39 over 11. So we just keep track of the sign, but we do the polarity as if it was, we weren't worrying about the sign of that initial condition. And what else do we have? We had a resistor across here. That's the top piece. We had another inductor over here and its voltage source. We had a resistor. We had a voltage source here, and we only have to worry about this one for positive time, and that was a cosine, so that's S over S squared plus 5 squared. We can fill in all of these. I'll fill these in, and you can too, and we can compare our work next time we're together. Thank you. Wow, I'm sorry. Thank you for being so patient. I will see you on Thursday.